All right. So there were a couple homework questions people had questions about. So let's look at this first one, which is question 4 from homework number 7 from Varn's class, which is the following. So Co-17C. Um, Today is the 23rd. So here's the question. It's find all equilibria of the system dx dt equal to negative 3x plus 5x times 7 minus x minus y, and dy dt equal to negative 4y plus 8y times 7 minus x minus y. Okay, so we'll find the equilibrium and then use the analytical approach to determine the stability, right? Whether it's a source or a sink or whatever. So we're going to set these both equal to 0. And here's where you kind of have choices. Now, well, yeah. So what I would probably see is either one of two things. From this first equation, factoring an x out and then simplifying the rest, and second equation, factoring a y out and simplifying this, or alternatively multiplying it through and then factoring the x out. I think it's actually easier to multiply it through first, so we'll do that. So the first equation is going to become negative 3x plus 35x minus 5x squared minus 5xy equal to 0. And then factoring, well, combining these together, that's a 32x. Second. And then factoring out an x, we can rewrite this as x times 32 minus 5x minus 5y equal to 0. Similarly, let me turn this on here. If we do the same thing over here, we're going to get negative 4y plus 56y minus 8xy minus 8y squared equal to 0. And we factor out, well, we combine these together, that's a 52y. And we factor out a y, we've got y times 52 minus 8x minus 8y. And now we're in the position where we have both of our equations equal to 0. They factored, so we're going to essentially set each factor equal to 0 and find out what our equilibria are. So the easiest one is to set this factor and this factor equal to 0. And we're just going to get x equal to 0 and y equal to 0 for an equilibrium of 0, 0. Okay, so basically you're playing like a pairing game, right? It's one of these with one of these. So x is 0 and y is 0, or the second one is x is 0 and this equation is 0. 52 minus 8x minus 8y equals 0. But we just said x was equal to 0. So the 8x part doesn't contribute anything. So that part's just going to go away. And we're going to solve for y. We're going to get 52 equal to 8 times y. We're going to get 52 divided by 8 is equal to y, which reduces to 13 over 2. So our second equilibrium is 0, 13 over 2. Third one is pretty similar. Now we're going to plug in y equal to 0 and this part equal to 0. So we're going to get y equal to 0 and 32 minus 5x minus 5y equal to 0. But again, y is 0. That part goes away. You're left with 32 minus 5x equal to 0. So 32 is equal to 5x. So 32 divided by 5 is equal to. So we get 32 over 5, comma 0 is our third equilibrium point. And I will tell you before we look for this last one, that is the last one. We don't end up getting another one from setting this equation equal to 0 and this equation equal to 0. Here's why. Those are parallel lines. If you look at those lines, so before we do this, which we are going to do it, but I just want to point out, notably, in both equations, x and y have the same coefficient, right? You have a negative 5x and negative 5y, you have a negative 8x and negative 8y. So if you were to try solving either one of these for y, you'd end up getting y equal to negative x plus something. And if the plus somethings are different, those lines are parallel and they never intersect, so you don't get another simultaneous solution to both equations. And that's what happens here. So if I set 32 minus 5x minus 5y equal to 0, and 52 minus 8x minus 8y equal to 0. And I solve for y, I'm going to get 32 minus 5x equal to 5y, and then, can you see that? Sorry. 32 fifths minus x equal to y, or negative x plus 32 over 5. Similarly here, if I solve for y, I get 52 minus 8x equal to 8y. I get 52 over 8 minus x equal to y. And those are both lines that have a slope of -1, but a different line intercept. So they do not intersect. And I was pretty sure that was going to happen when I saw that they both had the same factor here. That's usually a good sign that that kind of thing is going to happen. All right, so we found all our equilibria. 0, 0, 0, 13 over 2, 32 over 5, 0. Now we have to classify them. Now, the person who emailed me about this question said that they were getting a weird result. They were saying they were getting an eigenvalue equal to 0. I worked through the problem. That doesn't happen. I think what was probably happening is they're just plugging in something wrong, or maybe took the partial derivatives in the wrong order. So let's be super careful when we find our Jacobian. So I point out, for finding the Jacobian, it's probably easiest to use these versions of the simplified function. So I'm going to say that my dx dt, which I'm going to call f, I like to use f and g instead of f1 and f2, but same difference. My dx dt is 32x minus 5x squared minus 5xy. My dy dt is 52y minus 8xy minus 8y squared. And then our Jacobian is going to equal partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. So in this particular example, it's going to be, let's see. So the partial with respect to x is going to be 32 minus 10x minus 5y. The partial of f with respect to y is going to be negative 5x. Partial of g with respect to x. And this is where, so I was actually doing this problem, and I actually did this out of order the first time accidentally. And I did get 0 as negative value. I'm like, I feel like I'm doing something weird. Because typically, when your two equations have, like, these two equations are pretty similar to each other, where like if you interchange x and y, they're kind of the same deal. And when that's the case, you would expect kind of the diagonal and off-diagonal elements of your Jacobian to mirror each other. So when I did this the wrong way, I accidentally got a negative 16y here. Or no, so I got it here, and it's like, that feels like the negative 16y should really be over there. And it should have been, or whatever I got should have been over here because I did it out of order. So I take the partial of this with respect to x, I get 0 minus 8y minus 0. And I'm happy about that because those look similar to each other. That's a good sign. And similarly, if I take the partial with respect to y, I get 52 minus 8x minus 16y. So yeah, when I did it, I got these two out of order, and I was like, this one shouldn't be there. They should be diagonal matching. All right, now we have to plug in our eigenvalues. So if we plug in 0, 0, we get 32, 0, 0, 52. So both of our eigenvalues are positive, which means we have an unstable node, also called a source. If we were just talking about stability versus instability, we would say our trace is positive. Our determinant is also positive, although this part here is leading to an unstable result. All right, looking at the next equilibrium point, which is a little bit more challenging. So we plug in 0, 13 over 2. Now, what I really want to point out here is you don't maybe necessarily have to find the actual values here. So here's what we're going to get. This one's kind of the diciest. We're going to get 32 minus 0 minus 5 times 13 over 2. 5 times 13 is 65 over 2. And then we get a 0 here. That's a good sign. We know if we get a 0 there or there, our eigenvalues are just the diagonal elements, right? I didn't even do the work of finding the eigenvalues in the last one. I just said they're 32 and 52. You guys believe me because you should. And then down here, we're going to get a negative. So what I'm going to really point out here is whatever is down here doesn't matter, right? Once you have a 0 there, I don't really care what ends up over here. I'm still going to write negative 8 times 13 over 2, but I'm not actually going to think about that because it absolutely doesn't matter. And then over here, we get 52 minus 0 minus 16 times 13 over 2. Yeah, it's kind of gross. So I do need to simplify these to know if they're both positive or negative or what. So 32 minus 65 over 2, that's actually very, very slightly negative because 65 over 2 is 32.5. This is negative 0.5, 0, don't care. And 52 minus 16, 62, 16 over 2 is 8. 8 times 13 is bigger than 52. So I know that this is a negative number. It's 52 minus 8 times 13, which is 104. It's actually negative 52. But I could have really just stopped and said, cool, I know it's negative, and then my trace is for sure negative, or I should say both my eigenvalues are negative. So lambda 1 and lambda 2 are both negative. We have a stable node, also called a sink. If you were just talking about stability or instability, you could see, well, the trace is a negative 0.5 plus another negative number, which is negative, and the determinant is a negative 0.5 times another negative number minus 0 times whatever. That's going to be a positive number. So we meet the criteria for stability. Our trace is negative, our determinant is positive. So we could also just use that to say, cool, it's stable. We can't say what kind of stability, which is what I think we should actually be doing personally, but that's not how the problem's written. But we can say it stays. And then for the last one, which was 52 over something, where'd you go? 32 over 5, comma 0. So plugging in 32 over 5, comma 0, we luckily get the same sort of result. So I'm going to get 32 minus 10 times 32 over 5 is not bad. It's 64 because it's 2 times 32. And then here you're going to get a minus 5 times 32 over 5, which is okay. That's not hard to calculate. It's minus 32. Down here, you're going to get a 0. Hooray! And over here, we're going to get 52 minus 8 times 32 over 5 minus 0. So we get negative 32, don't care, 0, and is this number negative or positive? Well, shoot. 52. I guess I should get a common denominator, multiply 52 by 5 over 5. You know what I should really do? Should I? Yeah, sure, 5 over 5. So 5 times 52 is 260. So 260 over 5 minus 8 times 32 is... 8 times 30 is 240. 8 times 2, 240 plus 16. That's often how I'm actually doing multiplication like that, if the numbers are not terrible and overlapping. So this is very slightly positive, meaning our eigenvalues are 1 negative, 1 positive, so we have an unstable sink. That's saddle. And we could also say, oh, our determinant is negative because negative times a positive minus 0. So that's how we should approach questions. And I do want to point out to whoever was that sent me the email to ask me, none of the eigenvalues do end up being 0. I think what probably happened when you were trying it before is you might have just either interchanged where part of the Jacobian went, or maybe plugged in the wrong number somewhere and gotten a 0 where you shouldn't have. Sure, the original system was, so my original system was this. And yes, I do recognize that WebWork gives different questions to different people. So my original system looked like that.
Because I was checking the problem.
Like right.
So that's what I've done.
So yes, you'll have to do your own work for your own particular setup. But I'm pretty confident that if it looks similar to this, which it should, you should get similar results. And none of the eigenvalues should be 0. All right, let's look at this other question that was asked about, so this was another homework question. I'm not sure which one it was, but here, and again, I really couldn't imagine you being asked to do this on an exam, but this is not an exam, so this was asking us to find the function, the y equals f of x, that represents our equilibrium or equilibria, because this system of equations, and this does happen sometimes, you can have an infinite number of equilibrium points. It's kind of weird, but it can happen. Just like there are functions where you can have an infinite number of minima. You can have, you could have like yeah, there's some weird ones. I don't really want to get into it right now, but there are definitely some functions that have like you can have like a circle where every like the surface like kind of comes down like this and then bottoms out in a circle and then turns back around and goes up. So that circle is an infinite number of relative or absolute minima. In a similar way, you can have an infinite number of equilibrium points. So we're just going to start off as usual, set them both equal to 0. And the first thing I should do is try to factor stuff. And I can see here from this first equation, I can factor out a y, so I will. So you get y times y minus 4x squared minus 5x. And over here, I see what's going to happen. I'm going to factor out an x, and I'm going to get, not surprisingly, the same thing. Y minus 4x squared minus 5x. So again, so this question only asks you to find this part, but I'm going to find all the equilibria because, of course. So one of the equilibria is going to be, well, oh, that's interesting. Well, so I'm going to do the thing, but then I'm actually going to regret it, so it's okay. So one of the equilibria is 0, comma 0. So we set y equal to 0 and x equal to 0. That works. One of the equilibria is if I set x equal to 0, and then if I set x equal to 0, if I pull that in here, I'm going to get y minus 0 equal to 0. So I still get y equal to 0. So that's still giving me 0, 0 as an equilibrium. And in a similar way, if I set y equal to 0 and set this part equal to 0, I'm also going to get 0, 0. So the thing that I recognized when I saw that is 0, 0 is one of the equilibria we're going to get by setting both of these parts equal to 0. So if we set this equal to 0, and I'm not going to write it again because it's the same factor, I'm just going to solve for y and say, weird, this whole equation, this whole parabola, every point on that parabola is an equilibrium of this system of nonlinear differential equations. Kind of interesting. So what that means is like if you were to plot this on one of the field generating plotting systems, you would have like a parabola of equilibria where everything was either, well, I don't know if they're stable or unstable. Everything would either be going in towards it or going away from it. So funky. But that's the answer to that question. It's just it's y equals 4x squared plus 5x. It's kind of weird. You have a question, Kelsey?
Oh, yeah. I wanted to go over,
Oh, from the practice exam, right?
yeah, number 3.
The more recent one?
Yeah, the one that you put up for
Cool.
bonds.
Oh yeah, this bacteria in two different places thing.
Yeah.
Sure. Oh, there's a question in the chat. 1 second. Could you go over 5x? Possibly. Yes. Although I'll say that problem, so the person in the chat's asking me about looks very similar to the one we did just a minute ago. Although it's a little bit different, but it's the same vibe. But yes, we can take a look at that in a moment. So this is number 3 from the more recent practice exam, which is very wordy. So here's what it says. We have bacteria in 2 different patches, A and B. And the challenging part here, I think, is actually setting it up. The rest of it's not bad, but making sure you're reading what's happening correctly is a little challenging here. So it says, the bacteria in patch A are increasing in number at a rate of 4 per capita. So that means every bacteria in every bacteria in patch A is essentially creating 4 more bacteria per capita in some unit of time. So what we're going to say is that we know that and I think I used x sub A, not A, apologies. dx sub A dt, well, it's increasing by 4 times whatever x sub A is. Holy geez, let me write that again. Sorry, I got to use the right notation here. Apologies. We have bacteria A and B, and we're saying that dx sub A dt is equal to 4 times x sub A. And moving to patch B at a rate of 2 per capita. That part of that description here doesn't go in this equation, right? We're saying B is increasing at 2 times the amount of bacteria in patch A. So we could say for the rate of change of x sub B, the bacteria in patch B, it's going to be 2 times x sub b. Reading on, the bacteria in patch B are growing in the number at a rate of 4 per capita, so they're also increasing at 4 times their own selves, and moving to patch A at a rate of 3 per capita. So the XBs are increasing the XAs at 3 times however many XBs there are. That's how this is getting set up, which hopefully is how I did it when I wrote the solutions.
That's really like this subtract. So I think for me, like my question was like, why wouldn't you subtract the ones that are leaving as well?
Yeah, I had.
That's a good question.
Cause I had,
Yeah,
I had
did I think of this the wrong way?
I had the exact same like.
Yeah. No, you make a good point.
This.
Yeah, so to be honest, I didn't think about that when I was setting it up. So if we're drawing a compartment diagram, so we've got our X sub A's here, and our X sub B's here. Yeah, you make really excellent points. Apologies for my oversight there. So yeah, so let's read this again with a better eye. All right, so we have bacteria in patch A are increasing in number at a rate of 4 per capita and moving to patch B definitely says we're losing them. So we have, right, these are growing at, it's like self-referential here. These are growing at 4 times XA. And then we said that the in patch A are leaving to patch B at a rate of 2 times. Yeah, I can't argue with that. It's very correct. And then from XB to XA, we have where they're growing at a rate of 4 per capita. And then we're leaving at a rate of 3 per capita. Yeah. So we should have here that dxa dt is actually equal to 4xa, oh, that should be a b there, sorry. 4xa minus 2xa, so 2xa plus 3xb, and dxb dt should equal 2xa plus 4xb minus 3xb. Yeah, good call, everybody. So that means our matrix should actually look like 2, 3, 2, 1, which someone did email me about, but their question didn't seem super clear to me. So I responded that, well, none of these matrices look like what I have. So I didn't realize that that's what they're saying, that we should be looking at that. Apologies to the person I didn't believe about their email or didn't understand what they were saying about their email. So to answer the first question, to construct a system of linear differential equations to describe the above text, well, there it is. So this is the answer to the first question. Except they say do it in matrix form, sorry. So in matrix form, it should look like dxa dt, dxb dt equal to 2, 3, 2, 1 times xa, xb. That's the answer to the first question. And in part B, they say find the eigenvalues. And then I'll point out, they don't say to find the general solution. They just say to find the eigenvalues and then determine the type of local stability. So let's do that. Shouldn't be too terrible. So part 2, eigenvalues, determinant of 2 minus lambda, 3, 2, 1 minus lambda, not times anything, just equal to 2 minus lambda times 1 minus lambda minus 2 times 3 equal to 0. We multiply this out. We get lambda squared. We get minus lambda minus 2 lambda is minus 3 lambda plus 2 minus 6, 0. So that's lambda squared minus 3 lambda minus 4 equals 0. That factors as lambda minus 4 times lambda plus 1. So we got one of each. We have lambda equal to positive 4 and negative 1. So we have a saddle. Good call. As I would say in general, if you ever see something you think is a mistake, you should email me about it. But clearly someone did, and I just didn't understand what they were saying. That said, you should still let me know. If you see something you think is wrong, don't hesitate to ask me because clearly I can make mistakes. Happens. Question.
Matrix form is with the dx, the like.
So I would write it like this. You could also alternatively have written as dx dt equal to the matrix 2, 3, 2, 1 times the vector x. That would also be just as good.
A equals 1 mark.
No, you have to write because it doesn't say write the matrix. It says construct a system of linear differential equations that describe the above text in matrix form. If you just write the matrix, although it's representative of that system, you actually need to write the vector equals the matrix times the vector to actually represent this system of equations. Even though we 100% of the time are like, yeah, the matrix is what it is, and we know that it means the other thing. But your teacher wants to make sure that you know that it means that thing. So they want you to be able to say, oh, yeah, I know we're really talking about this system of equations, which can be written as this matrix equation here. Fair question. All right. And then here's another one. Again, this next one that someone asked via the chat is similar to the ones we looked at, but it's good to see it again. So asking again how to find and classify the equilibria for this non-linear system of differential equations. Dx dt equals 5x times 5 minus x minus 9y. Dy dt equals 7y times 8 minus 3x minus y. This one's going to go very, very similarly to that first one we did with one exception. Well, a couple of exceptions. We don't have to multiply anything out in the first place. Like, we don't have to factor out an x or y from the thing because it's already kind of factored nicely for it. But in this problem, let me ask you, when we set both of these more complicated parts equal to 0, are those lines parallel or not? They're not, because we can see that essentially the ratio of the coefficient of x to the coefficient of y isn't the same in both of these equations. In the previous one, it was 1 to 1, or -5 to -5, or -8 to -8. And since the ratio was the same, I was pretty confident the slopes of those lines were going to be the same, and they were either going to be the same line, which would be terrible because then you'd have an infinite number of equilibria, or parallel lines, meaning you wouldn't get another equilibrium. So if you can recognize pretty early on that these have different slopes, you're pretty confident that, okay, we're going to get an equilibrium by setting that equal to 0 and that equal to 0. Well, let's do the easy ones first. We're going to set 5x equal to 0 and 7y equal to 0. And not surprisingly, we're going to get 0, 0. Then we're going to set 5x or just x equal to 0 and the other equation equal to 0. So we're going to get 8 minus 3x, which is 0, minus y equal to 0. So we get y equal to 8. Switch it up. We set 7y equal to 0 and 5 minus x minus 9y equal to 0. So y equals 0 and 5 minus x minus 0 equals 0. So 5 is equal to x. So we get 5 comma 0. And finally, the one that's some amount of work here, we set 5 minus x minus 9y equal to 0 and 8 minus 3x minus y equal to 0. In this case, it's pretty easy to isolate either x or y and plug it into the other equation. I'm going to isolate x over here and say 5 minus 9y is equal to x. And I'm going to plug that in for x over here. So I have 8 minus 3 times 5 minus 9y minus y. Make sure your y's and your 9's look different. Equals 0. Multiplying it out and solving, we get 8 minus 15 plus 27y minus y equals 0. So we get 26y over here equals 15 minus 8 is 7. So we get really, really nice numbers here. Y is 7 over 26. Ugh. And then we plug that back in over here to find x. Gross. So the next is going to equal 5 minus 9 times 7 over 26. Multiplied by 26 over 26. What's 5 times 26? Better question. Or no, a better way to do it. Instead of multiplying by 5, multiply by 10. What's 26 times 10? Divide by 2. 130. So that's what we're going to get here. So 5 times 26 is 130 because we multiplied by 10 and then divided by 2, which is the same as multiplying by 5. So you're going to get 130 over 26 minus 63 over 26, which is going to be 67 over 26. So there's our third terrible equilibrium. 67 over 26, comma 7 over 26. Yeesh. And then the usual process for finding the Jacobian and checking. Now, I will point out, I would rather not use the product rule to find my Jacobian. I think it makes a lot more sense to just multiply out that our first thing, which I'm going to call f, is 25x minus 5x squared minus 45xy. And G is 56y minus 21xy minus 7y squared. So then my Jacobian is going to equal partial left with respect to x, which is 25 minus 10x minus 45y. Partial with respect to y, which is negative 45x. Partial of g with respect to y, which is gross. No, it's not. No. So that's right. That's the mistake I made last time. I was getting in the second row. I did the partial of g with respect to y first instead of with respect to x. It's always x first, y second. The x with respect to x in the first column, with respect to y in the second column. So partial of g with respect to x is going to be negative 21y, and partial of g with respect to y is going to be 56 minus 21x minus 14y. Goodness gracious. Okay, 3 of these should be easy to plug in, the ones that have a 0 somewhere. So I plug in 0, 0, I'm going to get a nice matrix, relatively speaking. It's 25, 0, 0, 56. So we have an unstable node, or just an unstable equilibrium, because their eigenvalues are both positive. And then if we plug in 0, 8, we're going to get 25 minus 0 minus, So I'm going to look ahead. I'm plugging in 0 for x, right? So I can see I'm going to get a 0 there, which means I know I don't need to worry about my off diagonals. So and I really just have to worry about the signs of things. So I'm going to say, great, this is 25 minus 45 times 8. That's going to be negative, right? 25 minus 45 times 8. 45 times 8 is way bigger than 25. I'm plugging in 0 for x here. I'm going to get 0 for that. I plug in 8 here. I don't really care what negative 21 times 8 is, because this doesn't change anything. And then over here, when I plug in 0 for x and 8 for y, I get 56 minus 0 minus 14 times 8. Okay, so I'm going to point out we have a negative number, a 0, a number we don't care about, and a negative number. So both of our eigenvalues are negative. And I have a fairly strong opinion that this would be sufficient, that you don't actually need to, on an exam, calculate those numbers because you're not being asked to. Or for homework, right? They're not, well, no, for homework, yeah, you don't need to calculate those values either. They're not asking you to actually write what the Jacobian is. Just use the Jacobian as much or as little as you need to determine the quality of your equilibria. So here we're going to have a stable node. But I really do think if someone asked a question like this on an exam, it would be fine to write exactly what I've written and not do anything more than that. Then for the other one, which is also going to be not terrible, for 5, 0, we're going to go, let's see, x is 5. So again, I'll point out we're going to get a 0 in one of those two spots, so we're happy about that. We've got a 0 there. We've got a negative 45 times 5 over here, which doesn't really matter. But then in the first spot here, we have 25 minus 5 times 10. Okay, that's not terrible to calculate. 25 minus 50 is negative 25. And then got that. And then here we have a 56 minus 21 times 5. I know that's 21 times 5 is somewhere around 100. 56 minus, that's certainly going to be negative. So over here, I also have a negative number, a whatever, a 0, and a negative number. So again, also a stable node. And now for the last one, the terrible one. 67 over 26, comma 7 over 26. Yeesh. All right, I'm not feeling great about this, but let's do it. Okay, so 25 minus 10 times x is going to be 670 over 26. And 45, oh my God, times y is going to be, let's see, 45 times 7 is 280 plus 35 is 315 over 26. This is going to be terrible. And then negative 45, this is where you should use a calculator. And then negative 21 times 7 over 26, and then 56 minus 21 times 67 over 26 minus 14 times 7 over 26. And then you know what to do. Find the eigenvalues. Or use the trace determinant method if it's that kind of question. So either find the eigenvalues. It's probably a find the eigenvalue situation. I'm not going to do it. You can do it on your own. It's terrible. Definitely a problem where you should use a calculator, right? You shouldn't be doing the rest of this by hand. Neither should I.
Like how many equilibrium you're supposed to have.
Okay, so the only time you should have more than one is in this sort of situation when it's a non-linear system of differential equations, right? For a linear system, whether it's homogeneous and you have the origin as your equilibrium, or non-homogeneous and you have a different point as your equilibrium, then you do the change of variables to move it back over to the equilibrium, those systems have one equilibrium. The only time you have multiple is non-linear. To know how many you have is another question that's not easy to answer. But it looks like a lot of the time we're encountering the situations where you essentially have both differential equations factoring into kind of two pieces, and then you just combine each possible way that the first one and the second one can equal zero. But definitely factoring each of them is vital. You need to factor them so you can see, okay, well, what's going to make this one zero? What's going to make that one zero? Yeah, but it is, I mean, it is really, it's never the same exactly every time, right? Because it's always like, well, this one's a little bit different. And sometimes, like, for example, I would just point out, so let me show you two made up things that are not really differential equations, but you could kind of encounter and kind of see the difference. So let's say this was one of our systems. We had dx dt equal to, I'm just pretending, well, I guess it's not really pretend. I have like, here, what? 5 minus x, y plus 2, and dy dt is equal to x minus 3 and y minus 7. And I want to find the equilibria. All right. How many am I going to get? And this is a trick question. I want you to think real hard about what x and y can be to make both equations equal to 0 at the same time. Okay. You thought about it. My claim, there's two. Here's why. So if I set the first equation equal to 0, I can set 5 minus x equal to 0. Or y plus 2 equal to 0. In the second equation, I can set x minus 3 equal to 0 or y minus 7 equal to 0. But there aren't four pairings here because I can't pair y minus 7 equal to 0 with y plus 2 equal to 0. That doesn't give me an equilibrium. In fact, that's not going to work because y can't be 7 and negative 2 at the same time. So the only way that this one actually gets an equilibrium is if I have this with that. So x equal to 5, y equal to 7, so 5 comma 7, or this with that. X equal to 3, y equal to negative 2. There's no other combination of values of x and y that makes both of these equations equal to 0 at the same time. Yeah.
Is that just because, like with one set, or like with one equation, you can't
really plug it in. So
Yeah.
let's say like if I set this first, if I said like, okay, I'm going to pick x equal to 5 for the first one. If I plug that into the second one, well, then that's going to be 2 right there. And the only way the other equation gets to end up equaling 0 is if y is 7, which is one of my equilibria. But if x is 5, the only way you get equilibrium is if y is 7.
You said there's only one equilibria, like linear.
Right, because this is a non-linear system of differential equations.
Linear have like more than, or have exactly one equilibrium, or
Yeah, it could. Yeah, you could have, but before I answer that question, or before I give you an example, let me just show you how, if I were to just change the system slightly, it's very different. So I had dx dt equal to 5 minus x times x minus 3, and dy dt equal to y plus 2 times y minus 7. Now I've got a whole lot more equilibria, because I could have 5 comma negative 2, or 5 comma 7, or 3 comma negative 2, or 3 comma 7. So you're just trying to find all the ways that both equations get to equal 0 at the same time. As far as nonlinear goes, as far as having you can, it's not super typical, but you could have something like, sure, I mean this is gonna be kind of boring, but you could have something like dx dt equal to sure xy minus 9 and dy dt equal to, I'm gonna make it real boring, x minus 3. Not super exciting, but it is nonlinear because I have an x times y. That makes it nonlinear. It's also not homogeneous, but who cares? So I'll point out the only way we're going to get an equilibrium here is if, well, what is x going to have to be? 3. And if x is 3, well, then y is also going to have to be 3. So here, my only equilibrium for this nonlinear system is the point 3 comma 3. So yes, it's possible, but it's not typically what we see. Yeah. Yeah. Say that one more time. Sure. So complex. Yeah, complex. So let's say our system. So I'm just going to write the matrix for the system. How easy am I going to make my life? Good question. One sec. Sure. Not very exciting, but fine. That looks very blurry. Okay. So here's our matrix and usual. So we're going to solve the system, right? Find the general solution. So eigenvalues. Determinant of -1 minus lambda, 3, -3, -1 minus lambda. That's going to be -1 minus lambda times -1 minus lambda minus 3 times -3 equal to 0. Again, if you happen to end up in a situation where these two factors are the same, you should do the thing where you're just going to say it's -1 minus lambda squared plus 9 equals 0. -1 minus lambda squared equals -9. Square root both sides. -1 minus lambda equals plus or minus the square root of -9, which is just plus or minus 3i. And then add lambda over there, bring that over there. So -1 plus or minus 3i is equal to lambda. And yes, you're subtracting the plus or minus 3i, but minus a plus or minus is still a plus or minus. So right away, we know we have a what kind of system for our, or what kind of equilibrium here? Stable spiral. Yep. Cool. So then the rest of this, which is terrible, is you gotta find the. So again, this is where, right, when it's complex like this, you only use one of the eigenvalues. It's the only time you do that. When you have complex eigenvalues, you use one of them. You find the eigenvector, then you do the whole Euler's formula breaking it up stuff. So to find our eigenvector, we're going to say that our matrix for lambda equal to -1 plus 3i. And again, I know I've said this every time, but there's no good reason to use the positive one. We just do. So my matrix is going to be -1 minus. Oh, no, if I'm doing it, I don't like doing it that way. I could do it that way, but I'm going to do it the way I usually do it, which is write the matrix multiplied by the vector we're looking for equal to my eigenvalue times the same vector we're looking for. And I'm going to use the first equation, which is -1 times x plus 3 times y equal to, I do think it's worthwhile to distribute the x to both of those. Instead of writing it as -1 plus 3i times x, I think it's better to write it as -x plus 3i times x, because then this part to this part, something a lot of times they cancel because of the way we set these problems, but sometimes they won't cancel. But either way, you're still going to be adding whatever the real coefficient of this is over to that side there to get something. So you want to break this part up like that anyway. So here we're just going to end up getting that 3y is equal to 3i times x, and I would divide both sides by 3 to get y equal to I times x. So in this case, our vector is going to be x is 1, y is I. I won't use the alternate one that I did last time accidentally. Something else I want to say. Just for completeness' sake, if my eigenvalue was -1 minus 3i, my eigenvector would be 1 negative I. Okay, so then we write the solution. And again, I will apologize. This is where I always get a little bit tripped up in how people like to do it specifically. So our general solution is going to be e to the lambda -1 plus 3i times t times my eigenvector, which is 1i. And I think we usually avoid writing the c in front of this until we get like to the end. That seems right to me. Some people, I don't know, it kind of, either way is fine. So then we break it apart. It's e to the -1 times t times e to the 3i times t, which I'm going to write as 3t times I. So that I'm being explicit about how I'm going to use Euler's formula here. And then I like to write this as just as is, but if you want, you can do the thing where you break this up as the real eigenvector plus I times the imaginary part of the eigenvector.
Does it make a difference if you just keep it one?
It does not make a difference. So then we multiply it out, or sorry, we write out what e to the 3ti is going to be. So this is going to become e to the -t times cosine of 3t plus I times sine of 3t. Still multiplied by either that or that. I'm gonna write it like, I don't know. The next step then is to multiply it through. So basically you're foiling this part out, right? It's these two things added together times these two things. So it's like this times this, this times that, this times that, this times that. Then we put all the real things together and all the complex things together. So we end up getting e to the -t times, the real things are cosine times 1, 0, and I sine times I times 0, 1, because I times I is -1. So it's minus sine of 3t times 0, 1. Plus, then we do the imaginary part. The imaginary part, I'm going to pull the out in front, is going to be cosine times I times 0, 1. And I pulled the I already. And then it's going to be I sine times 1, 0. And then typically, well, I know for Lee, I don't know for Vern, right? Then usually they like to say like, like, I guess I want the E to the, yeah. Sure. I guess I guess I should, here, let me scratch that. I'm pretending like those aren't there. I'm distributing the E to the -t. Sorry. I know it's kind of heinous. So then this is like my G of t. This is like my H of t. And my general solution is C1 times G of t plus C2 times H of t. Or you can just leave it like that.
If you were to keep the eigenvector, it's just
Like that?
one negative.
Mhm.
Can you maybe do it real quick?
Sure.
Because I don't know if the for the win is different.
It's not really, in fact, it's not really foiling at that point. So then you're just multiplying this by that. So you're getting in the first component cosine 3t plus I sine of 3t. And then in the second component, you're getting cosine of 3t times I.
Okay.
And you're getting I sine 3t times I. Which ends up being the same stuff, right? Because you've exactly got cosine times 1 and on top and negative sine times 1 on the bottom. And then you've got I times sine times 1 on top and I times cosine times 1 on the bottom. So same thing, just much more compact. In fact, I certainly would prefer to do it this way. I just know the instructors seem to like to write it that way.
And then you would just like, break that up into like the,
Yeah, and then you break it up into the real number. So and then there's this e to the negative t out in front. So then you would break this up as e to the negative t times cosine 3t minus sine of 3t plus e to the negative t times I times sine of 3t times cosine of 3t. And here's your g of t, including the I, there's your h of t. Sorry, the I is, sorry, not including the I, including the e to the t. There we go. Sorry, sorry, it's a little gross. Yeah, that's what you do. All right, good luck on your exam. We'll do fine. Or those of you that had an exam, I hope it went all right. And we'll see you all on Wednesday. Right? No class on Monday. See you all on Wednesday. Yes, yes,
Is there are going to be like any makeup at the end?
no,
No.
no.
Do like that times that.
So no, it's all of this times 1 and all of this times I.
I think that's simple.
Yeah, it is. It is simple. But it's it's not the way the book does it though, so I can see why the book would do it that way.
usually do conflict, I think. Some range of